In this video, we're going to go over a couple of example problems to do with the fundamental theorem of calculus part 2. So first we have the theorem, and it is that if little f is continuous on the closed interval a to b, then we have that the integral of f, the definite integral from a to b of f of x dx, is going to be equal to big F of b minus big F of a. Now this big F is just like the big F we saw in the fundamental theorem of calculus part 1. It's going to be an antiderivative of little f. And we can actually have any antiderivative of little f. So basically this part of the theorem gives us a really nice way to compute these definite integrals given we can find an antiderivative. It's a whole nother problem if we have a function we can't find the antiderivative, but for the ones that we can find the antiderivative for, we kind of have this procedural thing we can do. So we're going to start with an example where we're evaluating a definite integral. So we are looking at the integral from 0 to 5 of sine of t minus 6t squared dt. And so what we need to do is find an antiderivative of sine of t minus 6t squared. And we can do piece by piece. So the antiderivative of sine of t is going to give us a negative cosine of t. For negative 6t squared, we have negative 6t cubed over 3, where the 6 and the 3 simplify to a 2. And we're evaluating this from 0 to 5. So now that we have our antiderivative, we can go ahead and plug in our bounds. So we have negative cosine of 5 minus 2, 5 cubed, minus negative cosine of 0 minus 2, 0 cubed, which is just 0. So we get negative cosine of 5 minus 2 times 5 cubed gives us 125, so 125 times 2 gives us a minus 250. And then minus negative cosine of 0, well cosine of 0 is 1, so we have a minus negative 1, so plus 1. So we've got negative cosine of 5 minus 249. And that is going to be the value of this definite integral. All right, for this next example, I would suggest you pause the video and go ahead and try it. Okay, so this one might seem simplistic to just go ahead and routinely do, find the antiderivative of x to the negative 2, plug in the bounds, but for this one we have a problem, and we have to think back to what this theorem is saying, when we can use this theorem. We can use it when f is continuous on the closed interval, where these bounds of this closed interval are the bounds on this integral. So we need, wherever we're integrating, to be able to just use an antiderivative and plug into the antiderivative, we need for our function to be continuous on that entire interval, including the endpoints. And this one is not. So if you think about the way that this function looks, if we graph it, we have a vertical asymptote at x equals 0. So this function looks like this. And we're not continuous on negative 1 to 1. We're continuous on everywhere excluding 0. Well, 0's in that interval. So the fundamental theorem of calculus part 2 does not apply, as we have it stated. And dealing with integrals like this is actually going to be a Calc 2 problem. So you'll deal with this in Calc 2. There's more to say about this situation, but for now, in this class, we're just going to say that this integral from negative 1 to 1 of x to the negative 2 dx does not exist. It's not going to end up giving us a finite number, but for now we're just going to use does not exist. next problem is going to be an application problem with some physics. So we have the velocity of a ball is given by v of t is equal to 3t plus 1 meters per second. In the first part of this problem, we're going to write the function representing the position of the ball at time t, and we're going to assume that the initial position of the ball is s equals 0. So if you recall when we were talking about derivatives, we know that if we take position and we take the derivative, we end up getting velocity. And if you take the derivative of velocity, you end up getting acceleration, right? Well, that means that the antiderivative of acceleration is going to give us velocity, and the antiderivative of velocity is going to give us position. So what we can do is solve for our position function by finding the antiderivative of velocity, right? And we can actually set this up to be the integral from 0 to t of our velocity function. I'm going to use the variable x in here so that I'm not confusing the bound with the variable that's in my function. And I'll take the derivative with respect to x. And so here, when we calculate the antiderivative, we get 3 over 2 x squared plus x. We might have plus some constant from 0 to t. And when we go to plug in, we get 3 over 2 t squared plus t plus the constant. And then we're going to subtract off 3 over 2, 0 squared plus 0 plus c. Notice, just as a reminder, this is why we don't really have to write the c when we're calculating definite integrals, is because they end up canceling every single time. And we have this is 0, this is 0, of course. And so the antiderivative that we just got is 3 over 2 t squared plus t. And that looks like it's going to be our position function. We can double check that s of 0 is equal to 0, like how we said we can assume the initial position of the ball is at 0 by plugging in 0 and checking that we do in fact get 0, and we do. 3 halves 0 squared plus 0 does in fact give us 0, so we're good. We have the right function. If we didn't get 0, we would go ahead and make an adjustment, and we would basically adjust our constant so that we ensure that the initial position is the one that we were given. The next problem, we're going to be finding the displacement of the ball from t equals 0 to t equals 10 seconds. And then we're going to relate this quantity to a definite integral. Well, we have our position function. If we wanted to find the displacement, we could go ahead and take s of 10 and subtract off s of 0, right? That's exactly displacement. And we have the function, so we can go ahead and plug it in. So we're like, okay, this is 3 halves 10 squared plus 10 minus, and s of 0, we get 0 for all of those. So we get 3 halves times 100, which is going to give us 150 plus 10. So we've got 160 meters is going to be our displacement. Well, we want to relate this quantity to a definite integral. And for this, we're actually going to basically use the result of the fundamental theorem of calculus, which says that this displacement right here, s of 10 minus s of 0, this is nothing but the integral from 0 to 10 of our velocity function. Right? So we've got s of 10 minus s of 0. And this is just fundamental theorem of calculus part 2. Finally, we're going to find the average velocity of the ball over that time interval. And we're going to go ahead and graph the velocity and shade the region which depicts the displacement. So finding the average velocity, if you know the time interval and you know the displacement, you can find the average velocity, right? You would just take the displacement, which is 160 meters, and divide by the seconds, which we had 10 pass, right? We went from t equals 0 to t equals 10. And so this would tell us that our average velocity over that time interval is 16 meters per second. But now we're going to kind of relate that back to what we've been doing with integration, right? So we're going to graph, which we only need the first quadrant because we're going from t equals 0 to 10. And our velocity function was that 3t plus 1, which I'd have my y-intercept at 0, 1, and I have a slope of 3, so I'm rising. And this point is going to be up at 10, 31. Let's say this is 10. And we want to shade the region which depicts the displacement, right? Well, in part B, we talked about the displacement would be equal to this definite integral 0 to 10 of our velocity function. Well, we have graphed our velocity function. And this integral is nothing but the area underneath this curve. So in pink right here, this is going to give us our displacement. And there's actually one more area that we can graph that would give us our displacement that's related to the things we've already found. We figured out that the average velocity is 16 meters per second, right? So let's say about here is going to be 16. And actually, if I look at the rectangle where I'm taking our average velocity and I'm multiplying by this time interval, this guy is also giving us our displacement. So both of these guys give us our displacement.